Hello and good day to all. I'd like to talk about you today about the importance of electricity. Now, more than ever, we've been using electricity more than we've ever been, and that leads to higher electricity prices. And when we make electricity, we pollute the environment, so that also causes a bigger carbon footprint on the environment. But those losses are not just limited to electricity. We've got heat losses that are present when it comes to gas conduction stoves, whether they're in kitchens or in the industry or even in restaurants. You can find all types of heat losses on those, and we're going to focus on convection heat losses. Because we found a way, I think, to regenerate energy from all types of stove systems, whether it's in the industry or in the kitchen and all that. Since both of these statements clash with our SDGs, our goal will be to be able to reuse some of the wasted heat, because all this wasted heat clashes with our SDGs, so we can get closer to our sustainable goals. So our solution to this is a project that we made, which is called Stove Regen. And if you come and look at this right here, we've got two main aspects to this project. First, it's our TAC system. This pretty much works on temperature difference. This thing will get, on one side it's supposed to get hot air, on the other side it's supposed to have cold air, and the temperature difference will cause it to generate electricity, which we will then harness. But first I have to explain two sides. Why we have also this fin that will attach to the cold side, for better cooling, because fins have been proven to give more surface area, hence better cooling. Our second main component for this whole thing, as you can see, is our exhaust fan. So this is our Stove Regen system. It mainly acts as a exhaust fan to our system, which in most kitchens will need exhaust fans. So this will push our air onto the TAC. You cannot see the TAC because it's inside the case. It will push the air straight onto the TAC to cool it on the fin side. And the other side, the hot side of the TAC, will be heated by our stove or anything that acts under it. Generation, which will power our fan first, and secondary, all the excess voltage and electricity from it will go into a battery that we will store for more electricity to use. TACs. And we already know how the TAC works, but we want to focus on this design that all the air pushed through the casing, it will be forced out through this exhaust nozzle. And this exhaust nozzle is designed in such a way that the surface area starts shrinking at the beginning of it, and that forces the air to go at a high velocity. And right here, right at this point, it'll be at the highest velocity in our system, which will have the lowest pressure, because this system works on a pressure difference model. As our nozzle gets smaller and smaller, it starts to pick up pace. And right about our point here is when it enters the red zone, the highest velocity. It's where we've got our suction nozzle. And since we've got here the highest velocity, hence lowest pressure, we'll have here atmospheric pressure and low velocity. And what will cause this, because this pressure will be higher than this, it will cause a suction that will go through our suction nozzle and will exhaust straight out of our exhaust nozzle.
Now for the development process of the design. First we designed, as we can see on the left side, this is our first design, but when we tested it, it wasn't as efficient, or it wasn't working well as we wanted. And then so we changed design to be as the final design that actually works after testing it.